Today we are going to be learning about atomic theory. First thing we need to know about atoms is what they are and what they look like. So atoms are the smallest particles of matter that you can divide up using any physical or chemical means. Atoms are made out of three subatomic particles. The subatomic particles that atoms are made out of are the proton, the neutron, and electron. It is important for you to know where these subatomic particles are located, what charge they have, what mass they have, and what they do for the atom. So there's a table here that would be good to have in your notes. We have a picture here of an example atom. So first going through the protons, they are located inside the nucleus. They have a charge of 1.6 times 10 to the negative 19th coulombs. Now, a lot of times when we talk about charges, rather than talking about these Coulomb values here, actually it's more important just to look at, hey, protons are positive 1, neutrons are 0, and electrons are negative 1. When we look at the masses, again, a proton is about 1 AMU. When we compare a proton to a neutron, you can see that the neutron is slightly heavier, but not by much. When you look at an electron's mass, you can see the electron's mass is very small. It's essentially 0. So for the intensive purposes of what we're going to be doing here, we consider the proton and neutron to have the same mass, and for electrons to have a mass of 0. Protons determine the identity of the element. Neutrons determine whether or not the element is stable, and electrons determine the charge of the atom. We're going to take some time to just look at a simulator. And what we want to do is we want to look at what happens to the symbol, the mass number, and the net charge as we change the numbers of subatomic particles. First, if you can see that as I put a proton in, that gives, if you look at the symbol, an atomic number of 1, which is always hydrogen. Right now our mass number is also 1, and our charge is positive 1 because protons are positive. If I add a neutron, the atomic number doesn't change, it stays at 1. The mass number becomes 2 now because there are 2 nucleons inside the nucleus, and the charge stays positive 1 because the nucleus has no charge. If I add an electron, didn't quite get it. If I add an electron, the charge now becomes 0 because if you look, I have the same number of positives and negatives, so they cancel each other out. The mass number, however, does not change because electrons are such small masses. If I add another proton, you'll see not only does the atomic number change to 2 because now there are 2 protons, but also the mass number changes to 3. As I add another neutron, it changes to 4. As I add another neutron, it changes to 5. You'll also see that the nucleus becomes unstable. So there are certain combinations of protons and neutrons that are stable where others are not, and we'll get more into that later. So it's important for you to understand how to go back and forth between the symbols and the number of protons and neutrons. The general format for the symbol, I always like to say, is as easy as AZC. The A stands for the atomic number, which is the number of protons. The Z is the mass number, which is the protons and neutrons. And the C is the charge, which is the protons minus the electrons. X is just generically what the symbol is. So let's work a few examples. As I pull magnesium, the symbol out here, I'm just going to grab my pen, and we're going to try to figure out how many protons, sorry, I'm just writing with the touchpad here, neutrons and electrons this example has. So first, you always want to look at the atomic number. The atomic number of magnesium is 12. That means it has 12 protons. The neutrons, people are always tempted to say, well, if 12 goes here, then 24 must go by neutrons, and that's not the case. The mass is 24, And so the mass is protons and neutrons together. So I take 24 minus 12, minus the 12 protons that are already there, and that gives me 12 neutrons. Because the magnesium is positive 2 charge, it means it is deficient by 2 electrons. So that means I only have 10 electrons. We're going to clear this out and we will work another example. So hold on a minute as I delete this. Now we have a list of protons, neutrons, and electrons, and we need to figure out what should the symbol be based on these numbers. First, we look at protons because protons is directly related to the atomic number. Because the protons is 15, that means that the atomic number is also 15. We can go to a periodic table and look up what element is atomic number 15, and we will find that atomic number 15 is phosphorus, so that symbol is P. For the atomic mass Z, we looked that there are 15 protons and 16 neutrons. If you add these two together, whoa, that's really going to leave a big, sorry about the writing again. That's going to be 31 as the atomic mass number. And then finally, to get charge, I see that I have 3 electrons more than protons. That gives me a charge of 3 because of the extra 3 electrons, and negative because electrons are negative. There's a few terms you should know that go along with this. So the first one is, what is an ion? An ion is atoms with a net electrical charge. Atoms can become charged by either losing electrons or gaining electrons. If an atom has lost electrons, it will become positive, and chemists refer to that as a cation. If the atom gains electrons, then it becomes negative, and chemists refer to that as an anion. Atoms of the same element can also have different number of neutrons, which give them a different mass. That means you can have different atoms that are the same element that are called different isotopes. Isotopes are named based on their mass number. So for example, we can compare 2 isotopes of hydrogen. Hydrogen 2, because it is hydrogen, has 1 proton, and because it has a mass number of 2, it needs 1 neutron to complete that. Hydrogen 3 also has 1 proton because it is hydrogen, but now it needs to have 2 neutrons to add up to the mass of 3. One note is that people are always tempted to grab the masses for the symbols off the periodic table because the periodic table does have an atomic mass listed. However, this is not the mass that would ever go on a symbol. The masses on the periodic table take into account the fact that the protons and neutrons do not have a mass of exactly 1 AMU. They also take into account the fact that they are showing the average of all the isotopes that are available in nature and not just a single isotope. The nucleus is held together by the strong nuclear force. If the strong nuclear force wasn't there, the nucleus would rip itself apart because of the positives of all the protons mutually repelling each other. Some nuclei are not stable and can decay. They can do this in 2 different ways. If a nucleus has too many protons and they are pushing each other apart too much, the nucleus can undergo alpha decay, which is emitting an alpha particle, otherwise known as a helium nucleus. If the nucleus of an atom has too many neutrons, it can undergo beta decay, in which case a neutron decays into both a proton and an electron, and the electron is given off, and that is called a beta particle. There is a graph that you could find if you're interested in what combinations of protons and neutrons form stable elements, and it looks like this. You can see that at low numbers of protons, you have about the same number of neutrons as protons, and as you go higher and higher, the line of stability deviates away from this. So as you get to bigger atoms, you need to have much more neutrons than protons to make this work. When dealing with different isotopes, there are 2 formulas that we need to use, and we need to understand what relative abundance is. And relative abundance is how much of each isotope there is in a sample. The two formulas are given here, and you'll need to make sure you get those down into your notes. I want to take a look at a simulation where we look at different isotopes. Okay, so here's an isotope of hydrogen 1. It has just one proton and it is stable. If I add a neutron, it becomes hydrogen 2. I just want to take a look. I forgot to pull these up. If I take the one neutron away and go back to hydrogen 1, you can see that this isotope of hydrogen makes up almost 100% of all the hydrogen in nature, whereas hydrogen 2 is a significantly smaller portion. If we go to carbon, the isotope of carbon that exists most in nature is carbon-12, and is almost 99% of the carbon. There's also an isotope of carbon-13, which is slightly over 1%. And there's a radioactive, you can see that the nucleus went to unstable, version of carbon-14 that is very small indeed. When we mix different isotopes together, you can see that you can take on an average mass. So here if I take two hydrogen 1s and a hydrogen 2, you can see that by composition, it's 67% roughly hydrogen 1 and 33% roughly hydrogen 2. The average mass, if you do a weighted average between those two, is 1.34, whatever, and that you would get by using the first formula you were given back in the notes. When we look at some example problems here, so here's an example problem where we were trying to find the average mass of a sample that is 45% carbon-12 and 55% carbon-14. The equation for doing this is here, which you were given earlier. When we go to plug in, first we need to decide which one is A and which one is B. It doesn't really matter for this problem. I will just arbitrarily choose this as A since that is the first, and this is B because that is the second. Now I will take and plug the numbers into the formula. The relative abundance of A is 45%. When you put this in your calculations, you need to put it in as 0.45 to put it as a fractional number, not a percent. Its mass you get from just the name is 12. B has a relative abundance of 55%, and it has a mass of 14. Okay, so you're taking 0.45 times 12 plus 0.55 times 14. When you do this, you should get an answer of 13.1 atomic mass units. You should try to do this on your own to make sure you are able to come up with the same answer. The other type of calculation that you need to learn how to do is calculate the relative abundance of an isotope based on an average mass. We can see here that the problem is asking what the relative abundance of chlorine-37 is. The equation, remember, says that the relative abundance of A is equal to this ratio of masses. Because chlorine-37 is the one that the problem is asking for, I need to set chlorine-37 as being A. So now when I plug in the numbers, the average mass is 36.2. Ignore that it says 35.2 underneath. And again, sorry, I realized I should have fixed this. I'm going to send that to the back. Okay, and as long as I've got that out so we just don't get confused by the fact that it says 36.2, we'll just get rid of that there. All right, so the average mass again is 36.2. The mass of B, chlorine-36 is B, so I put in 36 for mass of B, for both masses of B. And then I put in 37 for mass of A. When I solve for this, I get an answer of 20%, which you can see is already displayed mistakenly down here. And so you again should go through this calculation to make sure that you also get 20%. If you have any questions about this video, you can email me at ekehoe@jwp.k12.mn.us or just wait for class.